I talked about my simulation after class.
Yeah, of course.
Yeah, I'm getting really bad mesh conversions results.
Hmm.
It's just like silly stuff like this. Like, I don't know. Sometimes, you know,
Yeah.
because it isn't necessarily took every time, but this I think we're just my own. Forgetting how.
Yeah, my regret was not writing down the missions. Well,
Oh, yeah, yeah.
if I had that, I would have done so much better. I got so distracted for 10 minutes.
This one. This is the one thing. This is a complete failure. Yeah, I couldn't remember how to do it. I was like, hopefully it keeps pushing.
Yeah, you did well, man.
Yeah, thanks. So that-
So they stayed what's going on. I'm probably gonna study the day before. That's it. I'm not gonna put that much time in.
Yeah.
One thing I want to study is like the circuit one.
Oh, yeah, yeah, yeah.
That one, and then it's just be prepared. That's about it.
Yeah.
But I'm mad at that guy. There was a lot.
I don't know. Just don't do it. Pick one.
And that's what my dude
Yeah.
was like.
Just be like, no, no, I submitted it.
I know.
Yes. Make it work.
I've never missed an assignment.
Ever.
Not starting here. at
Now's your
CSU.
chance. I didn't.
Not here. High school, yeah, I used to, that was a piece of shit. in High school. But
Aren't
it,
we all?
yeah, but it changes once you start paying schools.
Yeah.
It's like, bro, that's my money. I'm gonna throw it away.
It's possible, but this is a joke.
Yeah.
It's not now, I feel bad about it, but like, I didn't take it seriously then. Oh my God.
It's right around.
I was like, I'm so sorry, but I think they liked it almost.
Because they agree.
Yeah,
They're like, yeah, this thing.
but it felt so bad, but it kind of like, it liked the mood almost, so it kind of made it not.
Yeah.
Just give me money, I'm so cool. I'm like, all right.
Like, why should you give me money? Because I'm poor.
But that's stuff in its own regard.
Oh,
I
yeah.
think I can do it. I was like, I can't read all of it.
Yeah, I agree. I haven't taken political science in the community. It's cool. Professor. Like, I don't see myself doing that. Especially now in today's political finance.
Yeah.
You guys must be suffering from migraines every fucking day.
You know who suffers like sat writers?
Oh, yeah,
Like,
it's too weird.
can you, yeah. How can you write sat writers?
It's fine. So how's your day been so far?
Yeah, it's been good. Winding down the semester.
Yeah.
I gave midterms in all my classes last week, and still I'm still trying to catch up on grading, but I'm on the last class,
Nice.
and so I'm grading that one now, and so I'm hoping to finish that before class tomorrow.
That 442.
Yeah,
Okay.
Yeah.
I felt well, but I'm gonna find out tomorrow. I guess. I got tripped up on like, the actual like writing equations problem. Yeah, it's it was something of information on it, so it's fine. But there wasn't a lot of questions by any means. but,
Yeah.
It's just hard to remember stuff
Yeah,
that we
yeah.
did a long time ago. I felt like I couldn't remember, even though I said.
Mhm.
But that's something I'm sure we'll find too.
I get it.
Yeah.
I've seen it.
I had to borrow like the presentation and stuff, but I shouldn't have. It's okay.
It's all right.
Take off.
Work that in.
Yeah, it really did. We were doing the math the other day, or yesterday, we Joshua calculated how much.
It's not. It's something else.
My brother asked me about the. You get probably work with the heck, and then like looking up on accident inflation. It's like, no.
Still gotta send out some IRA forms for reimbursement. I gotta get on that.
I have to send out all of mine because property. You just put stuff on one numbers everywhere. And you so many wrong. I'll do it. It's more or less straightforward. Also, you don't have to do it.
Yeah, exactly.
Yeah. Yeah, so.
So we'll go back. But it uses one as well.
Oh, okay.
It's on. So
They sell them at 5 different packs from Amazon. So it's nice. It's better than the cost of
Yeah.
Hold the gems in place, but it does often stuff. So that's some of my clothes. Wait, it's not like this. I recommend them to-
I was thinking about it later down the line. I
Yeah.
still need to get used to it once I get one eventually.
Have you decided on your weight to your girl?
Not yet, but she did give me her size.
Nice.
7.5.
She's still freaking out.
Not really. Oh, yeah. It was fun. Yeah, I'm pretty sure she brought it up with her family. It was Saturday. Well, last week was her birthday. And Saturday they were partying for her. Everybody got shit face after working her ass off.
Yeah.
And yeah, just joking around. Chris, yeah, stuff like that. And families joking around as well. I'm like, yeah.
That's hilarious. It's only been 10 years.
Hey, how's it going?
So,
Good.
I'm making that money. It's like, oh,
You gotta get one of the paychecks.
I told her, once I get my first paycheck, first thing I'm buying is a prenup.
Getting a lawyer. That's a plan, but I need to, it's. like we were talking about doing it like a month ago now, but now, so because I would basically be the only one.
It's different once you actually have.
I wouldn't, but I feel that I have a tendency to just like.
Once you actually have.
Yeah, but.
That's what I thought.
All right, it's 5:30, so let's go get started. Good evening, everyone. How's everyone doing today? Hanging in there, hanging in there. Barely. I hear you. I hear you. I'm like only halfway here today too. It's been that kind of semester, but we're almost there. You know, we have today. Hopefully today is going to be the last day of actual content, and then I don't know if we talked about this, but next week I just plan to have just work days on the project, and so you know, today we'll have, you know, we'll finish everything up with unsteady finite volumes, and then next week we'll just work on the project, and then, you know, hopefully that'll give you guys the time, you know, to get feedback from me and help each other out with the coding, because you know, I think one of the nice things about this project is that you know, everyone's kind of working on the same thing, and so you guys can help each other out through problems, which is always helpful. Yeah. Questions today will be a full lecture. Yes, I do plan for it to be a full lecture. Yes. And oh, I almost forgot again. And so I did want to talk about the finite volume part of the project because I forgot about it on Monday. And so today I want to make sure I do that before I forget again. Okay. Okay. And so with that, you know, we have a couple of things that are out there though. We have homework 6, which is due on next Friday. Okay. So I know some of you guys are working on it. I've answered a couple questions online about it already. And then from there, it's just the final project. Okay. And so are there any questions I can answer before we get started for today? Okay, all right, so first thing I want to talk about today is the finite volume part of the project. And so if you go to, I think the easiest way to find it is you go to the file folder on our Canvas site and you go to the project folder, okay? You'll see there are 2 files that are uploaded. And so there is a finite volume starter code. Okay, so very similar to the finite difference starter code. Okay, so you can go ahead and download that and look at that. But I think what's more important is I have an addendum, and so it's almost like an amendment to our project here. Okay, because the finite volume you're going to have to use slightly different values. Okay, and so you know, this has to do with the fact that, you know, when we do finite volumes, the way we handle Neumann boundary conditions are a little bit different than finite differences. And so just to make sure that you guys are getting something that's not, you know, that doesn't look like a total mess, I've modified the values here just to make sure that happens. Okay. And so the first big change that you're going to make is you're going to change the velocity magnitude. And so in the finite difference part of the code, you know, the velocity that you supply is just -1 for u, and for V is going to be sine of pi x. But for finite volumes, in order for you to get kind of a good solution, you're going to have to change the velocities and reduce them by about 90%. And so the U velocity is going to be a minus 0.1, and the V velocity is going to be at 0.1 times sine of pi x. Okay, so I think that's kind of the bigger change. And the other change that you have to do is, directly related to the Neumann boundary conditions, in that you have to change the magnitudes. Okay, and so I think in the first part of the program, when just one window is open, in the finite difference part of the code, I said you should use a Neumann value of 40. But for the finite volume part, you should change that to 10. Okay, so you're going to reduce it by a factor of 4. And then later on, when the second window opens, I think in the finite difference code, then I said to specify a Neumann value of 75. Instead, you're going to reduce that significantly and only supply a value of 20 instead. Okay. And again, both of these changes have to do with kind of the same thing, that, the reason is with finite volumes, we handle the Neumann boundary conditions a little bit differently. And because this particular project, I think more so than previous year's projects, it relies a lot on how much in this case, how much heat, how much temperature is leaving through those windows. And so if you don't make these modifications, it might look like that you might be getting a ton of heat loss to the room, which is a little bit too aggressive. And so, I kind of toned them back for the finite volumes just to make sure that you can see, the code evolve in each stage of the code. Okay. And so make sure you make these changes if you're doing the finite volumes. Either you're an undergraduate and you're just doing finite volumes, or you're a graduate student and you're doing both. Okay. And then the starter code is here as well. Okay, so the starter code, I think after today's lecture, it'll make more sense, because today in lecture we're gonna go over a 2D example of how to do unsteady finite volume problems. All right, any questions on any of this? Okay, all right, so let me go ahead and stop this, bring back the iPad. All right, question. So will the lowest homework grade be dropped? Yes, yes. I should have already set that up on Canvas already. So Canvas will do it automatically, and so it'll drop the lowest homework for you. Yeah. Yeah. So if you've done all the homeworks up to this point and you've done well, then in theory you can skip the final homework. But the final homework is directly tied to your project, and so I think it would be good practice to at least attempt the homework, or at least keep an eye out for the solutions when they get posted, so you can use that to help you out with the final project. Okay, so let's go ahead and pick up where we left off. And so I do want to rewind a little bit, because I know I kind of skipped a few steps here. And so what we were looking at was basically how to apply time marching schemes to 2D finite volume problems. Okay? And in particular, because this is the method I'm asking you to do in the final project, let's do implicit Euler time advancement. All right, so I want to start here because, like I mentioned before, a big part of your project is going to be to combine the higher order schemes together with these time marching. And so I want to go through the kind of the math and the derivation behind this, just so that it kind of gives you guys some help in doing that if you're going to use finite volumes for your final project. So let's go ahead and start with our governing equation here. And so our governing equation, we have partial p partial t plus nabla V times a phi, so that there's our convection term, right? So I'm writing our governing equations here in vector format. Okay, then we have our diffusion term. And then we have our source. Right, so here is our governing equation here. And so this is unsteady. This one right here is convection. This is diffusion. This is our source term. Okay. And so in true finite volume fashion, we're going to be integrating these, okay? Which we've done before. The only difference now is that we have this unsteady term here. Okay. And of course, after we integrate, we're going to apply our integral rules. And so that's going to be divergence theorem and trapezoidal rule. Okay. And so I want to take it up to this point. Okay. Because this is the part when you will start to apply the higher order scheme. Okay. So after you do all that, we've seen that kind of several times. We're going to end up with the following. And so we're going to have partial phi partial t. Okay. And we're evaluating this at the cell centroid. Okay, so that's what the C stands for. And then we multiply by the area of the cell. And if we assume that delta x and delta y are the same, then this is going to be a delta squared. Okay. And then we have our four integrals, right? And so these are our convection and diffusion terms on the four integrals on the four sides of the cell, right? And so we have, first we have the east integral. So we have phi sub little e times u minus k partial phi partial x on the east face, okay? This is multiplied by delta. Plus the same thing on the north face, and so we have phi n times v minus partial phi partial y on the north edge, okay? Multiplied by delta. Okay. Then the same thing on the west edge. Then the same thing on the south edge as well. And of course, this is equal to the source term. Okay. All right, and so you see kind of all four integrals here kind of all together in one equation, okay? And so I'm going to do something, I'm going to deviate from the class notes just a little bit, because in the class notes, what I did was after we plugged in for everything here, we simplified, we got just one kind of big equation for everything. What I'm going to do is just to kind of make it more consistent with the Matlab code that we're going to see later, I'm going to keep the four integrals separate, okay? And that's going to help us out with the, with how to interpret the code. Okay. Right. And so the next step is we need to plug in for all of the edge values. Okay. Okay. So that means all of these guys. Okay. And so this step right here, this is the main step that's going to deviate, when you apply your higher order scheme. Because right now we're just going to apply, fairly basic schemes for this. Okay. All right. And so if we do that, we get partial phi partial t, value at the centroid, delta squared plus. Okay. We have the values on the east edge. Okay. And so we have phi sub e, right? So that's the value of phi itself on the edge. And so here we're just going to apply our simple central scheme. And so that's just going to be the average between the two. Okay. And so we have phi sub big E plus phi sub C divided by 2. This is multiplied by U. Okay. And then we have K. Our diffusion term here, we're going to put our slope of the line with our linear interpolation. So we have phi sub E minus phi sub C, all divided by delta. Okay. And this whole quantity here is multiplied by delta. Okay. Plus, same thing for the north. And so for the north, we have phi sub big N plus phi sub C. That N looks like a W. Divided by 2, multiplied by V minus K, phi sub N minus phi sub C, all divided by delta, multiplied by delta. Okay. Then we have everything for the other faces. And so we have a minus phi sub big W plus phi sub C divided by 2 times U minus K, phi sub big C, phi sub big W divided by delta, multiplied by delta, okay. Minus phi sub big S plus phi sub C divided by 2, multiplied by V minus K, phi sub C minus phi sub S multiplied by delta, multiplied by delta. Okay. And all of this is equal to Q delta squared. Okay, so that's our source term. Okay. This is just a side note, we're not going to do it for, for this example, but everything that I've circled in blue right there, if you wanted to change this to a higher order scheme, you would replace everything in blue with the appropriate quick scheme. Okay. But for now, we just use the basic scheme. Okay. Okay. And so I'm going to go ahead and simplify this because everything within their respective integrals we can simplify a bit. Okay. And I'm going to do one more thing. And so I'm going to start to apply our time marching to this. Okay. Okay, so first we're going to simplify. And the other thing we're going to do is we're going to discretize our time derivative or discretize our unsteady term. And since we're applying this method as an implicit Euler, we're going to apply a time step of n+1 to all of the remaining phi terms. Okay. Okay. So let's go ahead and do that. And so first we have partial phi partial t, and so that's going to be replaced with phi sub c at n+1 minus phi sub c at n all divided by delta t. This is multiplied by delta squared plus we have everything here for the east integral. Okay. And so if we sum this up, we have two terms here. So we have phi sub e and phi sub c. Okay. So let's do the coefficient for phi sub c first. And so we have u delta divided by 2. I'm going to take this delta and multiply it in as well. Okay. Okay, so we have u times delta divided by 2 minus k multiplied by phi sub e plus u delta divided by 2 plus k phi sub c. Okay. So that takes care of the east integral. And we're going to have very similar expressions for the north, the west, and the south integral as well. Okay. And so for the next, we have v delta divided by 2 minus k phi sub big N plus v delta divided by 2 plus k times phi sub c. Okay. And I'm going to factor in the negative out in front too. Okay. So for this one, we have a minus u delta divided by 2 minus k phi sub w plus minus u delta divided by 2 plus k phi sub c. So that takes care of the west integral. Okay. Then we have the south one, and so we have a minus v delta divided by 2 minus k phi sub s plus minus v delta divided by 2 plus k phi sub c. Okay. And all that equals to q at xc, yc times delta squared. Okay. I know it's a lot right now, but I'm putting in this form just to kind of on purpose, because remember the way that we structure these MATLAB codes for 2D finite volumes is that we do one integral at a time. And so if we break up our algebraic equation to be in that same form, one integral at a time, then it'll make those coefficients a little bit easier to handle. Okay? In fact, let me color code this. And so let me put colored parentheses around all the different terms. Okay? And so in purple right there, we have the east integral. Orange. Orange here is going to be the north integral. Okay. Green right here, this will be the west integral. And the south integral will be in blue, just like that. Okay. All right, so keep those terms in mind. We're not done yet, but then after we're done, kind of keep those terms in mind as we go and fill out the MATLAB code. Okay. But all we've done so far is just kind of slowly and methodically kind of applied our process here, finite volume process to this equation. Okay. We have a little bit more to go until we get the exact coefficients that we need, but this is kind of a good start here. So are there any questions on this so far? Okay. All right, and so let's go ahead and work on this a bit more. And so let me go ahead and divide both sides by delta squared, okay, because we want to isolate that term. Okay. We're also going to multiply by delta t. Okay. And I said we were going to do it last step, but I didn't do it. And so we still need to apply time steps to all the phi terms that don't have it yet, but we'll do that in a second. Okay. Okay. So we're going to apply n plus 1 to all the remaining phis. Okay. This is for real. So for real, we're going to do it. Okay. And then last thing we need to do is that any phi term that has a time index of n, we're going to move it on the same side as the source. Okay. Right, so it looks like a lot, but a lot of them are just kind of small, simple changes. Okay. All right, so let's go ahead and do that. And so if we perform all those things, we're going to have phi sub c at n plus 1. Okay. So after we performed all those operations, the phi sub c at the from the time derivative just stays on its own. Okay. N plus. So I'm going to keep the same color convention here. Okay. So these will be the East integral terms. And so inside here, we're going to have u delta t divided by 2 delta. Okay. Remember, we divided by delta squared minus k delta t k delta t divided by delta squared. This is phi sub e. Let's go ahead and apply a time step on this side, and so that's going to be n plus 1. Okay. Okay. Then we have a similar term for phi sub c. Okay. And those are our coefficients for our east integral. Okay. Plus. Then we have our coefficients for the north integral. Okay. All right, so first we have v delta t divided by 2 delta minus k delta t divided by delta square. Okay. Okay, so that's going to be phi sub big N at time step n plus 1. Okay. Okay. Then we have the phi sub c contributions from phi sub n, okay, or from the north integral. Then we have the contributions from the south one. So we have a minus u delta t divided by 2 delta minus k delta t divided by delta square. I'm kind of checking my work as I go because this is different than what I have in my notes, and so I'm kind of doing this on the fly with you guys here. All right, and finally, we have the contributions from the south integral. So the south integral, which is in blue, this is minus v delta t 2 delta doesn't help that my Apple Pencils give me a big fuck you right now too. Come on, Apple Pencil. Drawing a triangle, not a squiggly face. How is that?
Isn't the green supposed to be the west?
Yes, it is. Thank you. Does it make sense to have you with this? Okay, so those are the four integrals, and then we have the right-hand side. And so on the right-hand side, luckily we have just q, xc, yc. Okay, the delta square is going to cancel out, but we still have a delta t that's multiplied by that. Okay, and we can't forget this. We need our current solution there as well. Okay. And so if you look back at our lecture notes from Monday, you know, I did try to get to this point on Monday, but I wanted to present it in a different form today because I think this form is going to be a little bit more useful because this is what we're going to plug directly into Matlab. Because I think the one I presented last time was just one big equation, which is good if you're going to do this by hand. But you know, realistically speaking, you're going to be applying this in code. And so I wanted to put it in this form just so you can see, you know, when we're doing the east integral. You know, these are the coefficients that we're putting in MATLAB, and this is the process that we took to get there. Okay, and when you're doing this exercise, if you're doing finite volumes for your final project, and you have to apply the quick scheme, right? You kind of know what process you need to follow. It's just that you make that one modification there. You know, instead of a central difference for the velocity, you're going to use a quick scheme there instead. Okay. All right, but here's the result. Right? So it's a lot of terms, you know, probably big. It's definitely bigger than the one we went off for on Monday. But you know, I think ultimately this one's going to be more useful. All right, any questions on this before we jump into an example? Okay. So let's go ahead and apply this in an example. So we'll do some hand calculations and then we'll go over how this is applied in MATLAB, just like we normally do. Okay, so let's consider the following equation. And so we have partial phi partial t plus 15 cosine of pi t times partial phi partial x plus sine of pi t. And so we have a time varying velocity for both the u and the v velocities, okay? And this is equal to our diffusion term, and so we have 3 has a mind of its own when I'm trying to write, but when I try to change the color, it doesn't respond.
Charge?
Yeah, it's fully charged. I heard Dr. Weiss is having issues with her Apple Pencil too, so maybe I'll ask her what she did. I know, right? That's valuable tax money that I spent on this thing. Okay. Just told my maybe. I mean, it's been having issues like this for the last few weeks. It's just now that I'm kind of at the end of the semester, I'm also at the end of my rope for the semester. It's bugging me now today more than it usually does. Okay. So of course, this is a different form of the equation than we usually have, but we can go ahead and label all the different parts. Okay, and so this 50 cosine pi t, of course, this is our x velocity u. This sine of pi t, this is our y velocity v. Okay, so these are time varying, and so we have to account for that into our equations. This 3 right here, of course, this is our diffusion coefficient, so this is k, and this 3xy, this is our source term q. Okay, and so we're going to apply our method here. Okay, so we're going to apply our 2D finite volume implicit Euler method to get their algebraic equations, and then we're going to see how this is implemented in Matlab as well. Okay. All right, so let's, I have to draw the domain. I haven't seen the domain yet. Okay. All right, so we have our typical square domain here. And so we're going to do it for 16 cells, okay? So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay? And for this problem, we're going to have Dirichlet boundary conditions all around, just because Dirichlet boundary conditions are a little bit more difficult to handle. Okay, and of course, another good reason why I split these up is so that when we apply our boundary conditions, we know which parts of this equation we need to modify. Okay, because this equation right here, even though it's very long, it's only going to be valid for our interior cells. Okay. And so I'll show you how to kind of by hand, manipulate this for the boundary conditions. But of course, we're going to do that in Matlab as well. Okay. And so here we have b is equal to 25, b is equal to 25, b is equal to 50, b is equal to 50. Okay. Let's say dt is going to be equal to 0.1, and do our dx. We'll say delta, oh, there it is. Delta is equal to 0.25. Okay. Okay, so let's apply this to interior cell 2, because that's just kind of more or less a plug and chug. Okay. And so let's do this for cell 6. Okay. Okay. And so since cell 6 is on the interior, we can just go ahead and plug everything in. Okay. And because there's some redundancy here, right? So because every integral here has phi sub c, right? And so after you plug in, you can of course simplify that and combine all the phi sub c terms, okay? Okay, and so I'm not going to have you guys watch me plug in stuff because that's it's going to take forever. And so let me just go ahead and skip to the final answer here. Okay, and so you plug everything in, then you get the following for phi 6. Okay, taking note, which what its neighbors are. All right, so this is going to be 10 cosine pi t minus 4.8 times phi 7. I wasn't even touching down there. And plus 1, okay, plus 0.2 sine of pi t minus 4.8. And this is for the north neighbor, and so this is going to be phi 10 and plus 1, okay, plus minus 10 cosine of pi t minus 4.8 phi 5 and plus 1. Okay, of course, that's the west neighbor. Then we have the south one. So plus minus 0.2 sine of pi t minus 4.8 phi 2 and plus 1. Then you combine together all the phi sub c contributions, and so you end up with 20.2 phi 6 and plus 1, okay, is equal to 0.3 xcyc plus phi 6 at n. Okay. And of course, we can simplify this even more because we can plug in the values for xc and yc. And so for cell 6, and so cell 6 is right here, right? And so for cell 6, xc is going to be delta plus delta divided by 2. And yc is going to be that as well. So delta plus delta divided by 2. Okay. And so if delta here is 0.25, this is going to be 0.375, 0.375. Okay. And so this quantity right here can be 0.375 squared. Okay. Okay. So that hopefully is pretty straightforward, right? And so we have our time marching scheme. It works for interior cells, and so we just go ahead and plug right in for that. Okay. Any questions on this? How I obtained this result? Okay. All right. So let's do a cell with the boundary condition now, right? And so let's do its immediate left neighbor. Okay. We're going to do cell 5, right? And so cell 5 here has a Dirichlet boundary condition on its west edge. Okay. Okay. And so you know what that means, right? And so if we have a Dirichlet boundary condition on the west edge, that means we have to modify the west integral. Okay. Okay. Right. And so our west integral, our result for that is normally phi w times u, excuse me, we have a minus out in front, right? So minus PW times U minus K partial phi partial X W, okay, times delta. Right, so this is after we plugged in everything. Okay, and in fact, just to make our lives a little bit simpler, I'm going to go ahead and apply some steps that we applied later, right? And so we're going to multiply this by delta t and divide by delta squared. Okay, and so if we do that, then instead of delta out here, we have a delta t divided by delta. Okay, and so this is a result of multiplying so that was a direct result of just multiplying by delta t and dividing by delta squared. Okay. Just want to draw a triangle, iPad, come on. Okay. And so that's so the reason I do that just so that we can kind of just accelerate this. And once we have this, then we come back up to this equation right here and use that to replace everything in green. Okay. Okay. And so if we modify this according to the Dirichlet boundary condition, right, that means phi sub w here, we're going to replace this with the Dirichlet value. And so this we replace this with phi sub w or phi sub naught. Okay. This here is our Dirichlet value. Okay. And of course, partial phi partial x. We're going to replace this with the shortened scope that we've done before, right? And so this can be phi sub c minus phi sub w, or phi sub c minus phi naught divided by delta divided by 2. Okay. All right, and so we plug all those in, and what we get is minus phi naught times u minus k minus 2k times phi sub c minus phi naught all divided by delta. Okay. We multiply this by delta t divided by delta. Okay. All right. And so if we multiply, that through, and then what we get is a minus phi naught u delta t divided by delta. Okay. Plus 2k delta t divided by delta squared multiplied by phi sub c. Then we have a minus 2k delta t divided by delta squared. Okay. Okay. And of course, every term here with phi naught, we're going to go ahead and move it to the right-hand side. Because remember, the left-hand side of the equation is reserved for n+1 terms only. Okay, and actually, I forgot to add that. And so this phi sub c here is going to be phi sub c n+1, of course, because this is an implicit limit. Okay, and so everything that's not n+1 are going to move to the right-hand side. Okay, and so that includes those two terms. Okay, and for cell 5, we know phi naught, and so phi naught for cell 5 is going to be 50. And so this expression right here. Okay. And so this is going to replace our west integral in our generic equation. Okay. And so what color do we use for west? We use green for west. Okay. So let me go ahead and color that green here. Okay. Okay. All right, and so if you do that, and you go ahead and move the term over like I mentioned there, then we're going to end up with the following equation. Okay. Okay. And so we plug everything in. What we get is 10 cosine pi t minus 4.8. We have our east neighbor, so phi 6 n plus 1. And we have our north neighbor, which is phi 9. And we have the south neighbor, which is phi 1 n plus 1. Okay. We don't have a west contribution, because the west integral doesn't exist anymore, or it did exist. We just removed it. Okay. All right. And then now our right-hand side of the equation is going to have a lot more terms because it has the Dirichlet boundary condition included as well. And so we have a 0.3 xc yc, okay, plus p5 to the n, right? So those are the usual contributions. And so usually we have our source term and our current time step solution. But now we're going to add our contributions from the Dirichlet boundary condition. Okay, so those are the two terms circled in red. And so if you plug in everything for that, you get a plus 1000 cosine pi t. Okay, I believe this is the first term, and so this is our phi naught u delta t divided by delta. And then we plug in for the other one, which is a 2 times k times delta t divided by delta squared times phi naught. You just get a flat 480. Okay. Okay, so this 480 right here, this is our 2k delta t divided by delta squared phi naught. It looks like we're going to end early today. Okay. All right. Any questions on this before we jump into the Matlab implementation? Okay. Okay. So the Matlab implementation, let me go ahead and scroll back up here. Okay. And so hopefully you guys have this part down in your notes right here. All right. And so what you'll see is that our Matlab implementation will mimic this very closely. Okay. And so if you think back to when we did our convection code for 2D finite volumes, you're going to see the structure here is very similar, except now we're going to add a time loop to it as well. Okay. And okay, so let me go ahead and share my screen. and I forgot to download the code. So let me go ahead and download it. All right, so we have 2D convection. Yes, this is the one we want. Download this. Matlab, which of course I did not have open. I'm a silly goose. Okay, let's go ahead and make this a bit bigger so we can see it better. Okay. All right, so here's our code. Okay. And so this is posted online. And so I just pulled it straight from Canvas. And so you guys have access to the exact same one. Okay. And so this is going to be the Matlab implementation of kind of what we just worked out by hand. Right? And so section 1 here, pretty standard stuff. We've listed out all of our problem variables. We don't have U and V here because U and V here, remember, are changing with time, right? So we have a 50 cosine pi t and a sine pi t for U and V respectively. Okay. And so we're going to implement that within the time loop because that's going to update every single time step. Okay? But for everything that stays constant, like the diffusion coefficient, like the time step size and t, we can go ahead and define it up here just to get it out of the way. Okay, and so here we entered the part of the rest of the code, right? And so just like normal for any time stepping problem, we have to specify our variables for sol next and sol curve, right? So remember that's phi n plus 1 and phi n. And then we enter the loop, okay? And so we have kind of loops on loops on loops, right? And so first we have the time stepping loop, right? And so this is going to time step in time. And so this is going to march sequentially. And so this is kind of what you normally see for unsteady problems, right? And so the first thing that you see that we do is we compute the U and V velocities, right? And so we have U is equal to 50 cosine pi t and V is equal to sine pi t, okay? And so the reason we have it here, right, is this needs to be inside the time loop, right? Because each time step, each time this loop iterates, this t variable here is going to update, right? So it starts at 0. If you scroll down to the bottom of the time loop, you can see here that we update it in t, before we enter the next iteration, right? And so for any quantities that change with time, whether be it a velocity or whether be it a boundary condition, you have to include that within the time loop. And so that's kind of what we have here. Okay. All right, next thing we do is I just simply reset the left-hand side matrices and right-hand side vectors just so that we're working with a clean slate. And so A is equal to 0, B is equal to zeros. Okay. And then we enter the space loop. Okay. And so just like we normally do with finite volumes, we have to visit every single cell. And so we have 4i is equal to 1 to nx and j is equal to 1 to ny. Okay. And then we compute our ID numbers, right? Okay, so here we enter the integrals, right? And so you can see I have four if statements here. Okay, so one for the east integral. I guess I do it a little bit out of order. So I do east, south, west, and north. Okay, but let's look at the east integral first, right? And let's look at the case when we have an interior cell, right? And so just like true finite volume case, we have two cases. So one where we have a boundary condition, and so that's the if statement. But the else is when we have an interior cell, right? And so that's this part of the code right here. Okay, so let's look at the coefficients that we have here, and you should see that they should match exactly what we have in the notes, with all the color coding. Okay, and so in my lecture notes here, I coded the east integrals in purple. Okay, and so you can see for the coefficient for phi sub e, I have a u delta t divided by 2 delta minus k delta t divided by delta squared. And so let's see if that's implemented here, right? And so our east ID, our east term is going to be this one right here, right? So you can see here, this is phi sub e. So there's a my ID east ID, a my ID east ID, okay? And so we have a u times delta t divided by 2 delta, okay? And then we have minus k delta t divided by delta squared. And so this is kind of exactly as we have it. Okay? And you can check and make sure that the phi sub c term is the same as well. So the u times delta t divided by 2 delta plus k delta t divided by delta squared, which is exactly what we have in the notes. Okay. And so, I know there's a lot of writing and a lot of deriving for that one, but now that you see that we have our finite volume equation in that form, we just kind of drop it right into the different integral expressions here. Okay, any questions on that? Okay. All right, and so of course, then we have our boundary conditions as well, and so this is the modification that we make for the boundary condition. Okay, so I know we only did one case with the boundary condition, but you can see those contributions here. Okay, and so I know we did cell 5, and so cell 5 is a boundary condition on the west side. Okay, and so the signs here might be a little bit different, but the idea here is the same, right? And so for phi sub c, we have a 2k delta t divided by delta squared. And then on the right-hand side, this is the b. Okay. We have a 25 times minus u delta t divided by delta x plus 2k delta t divided by delta x squared. And so remember, since we're working in MATLAB, you don't have to put in any hard numbers. You just have to set up the equations, and then MATLAB will fill that in for you. Okay. All right, so that's the east integral. So that's everything that was in purple. Okay. Next, we have the south integral. It's going a little bit out of order. And so this is the integral that I've circled in blue, right? And you can go through all these coefficients and verify that they're the same as well, okay? All right, same for the west, same for the north, okay? All right. And so the nice thing about finite volumes is that, you do kind of the boundary conditions and the interior kind of at the same time. And so by the time we reach at the end of these integrals here, all of our boundary conditions are taken care of, all of our interior cells are taken care of. And so the only thing that we have to add now is, just a few kind of extra terms. Okay. All right. So the first thing we add here is the coefficient of 1 on the diagonal. Okay. And so if you recall, when we discretize the partial phi partial t. Okay. So this is equal to phi sub c n plus 1 minus phi sub c at n. By delta t. Okay, we had an extra term of phi c n plus 1. Okay, and so we need to make sure we add that. And so if you look back in your notes, that's actually the very first term in the expression. And it's a little bit easy. It's kind of easy to forget about this guy. I know I do sometimes too, but we have to make sure we added it. Okay, and since that's going on the left-hand side, that means we have to add a coefficient of 1 to the diagonal. Okay, so that's what this line of code does. And so we have a maya d is equal to a maya d plus 1. Okay. And the last thing that you can see we're adding here is the contributions of the forcing function as well as the current solution. And so that's everything on the right-hand side of the equation. Okay. Okay. And so if you look at our equation again, you can see here we have a q xc yc times delta t. Okay, and so that's what this first term is. So this is q delta t. Okay, and of course the Sol curve ID, this is phi sub c at n. Okay. All right. And so there you have it. So that's our 4 integrals as well as our right-hand side equation. Okay. And so the last thing that we need to do here, of course, is to solve our equation. Okay. So this is pretty standard stuff. And so once we have our left-hand side matrix, the coefficients are settled, and we have our right-hand side vector. Okay. Then we just have to solve it. And so we go ahead and solve our equations. We do a backslash b. Okay. And so that's going to solve for Sol next. Okay. And after we solve for Sol next, then we just update our current solution. And then we go from there. Okay. All right. So let me go ahead and run this code. And of course, we can't forget to update the time variable. Okay. So let me go ahead and run this code. And hopefully it doesn't take too long to run. It's 30 by 30. Should be okay. Okay. And so I think we did this example before. And so I think back when we did unsteady problems for finite differences, we did this problem with kind of this undulating membrane. Okay, so that's kind of going back and forth. And you can see that we get the same results here in finite volumes. Okay, so let me go ahead and run it one more time just so you can see. Okay. Right. So if you compare this code, we did this. I think we did this exact same problem with finite differences, right? So finite difference, implicit Euler 2D. You should see the exact same thing, right? And so that's always encouraging with that. Okay. All right, and so that's all I had planned for today, and that's it. So we have no more lecture notes after this, and so that's 417 for you. And so, we do have some more time today. And so if you want to ask me questions on the project, either on Zoom or in person, I'm here for that. But, if you don't have questions, then, that's all we got for today. And so from here on out, we're going to have just project workshop time. And so, like I think I mentioned this on Monday is that, it's usually easiest for me, for me to help you if you come to class. That way, I can kind of look through your code and I can easily kind of point stuff out to you. But with that said, I will still help you if you're on Zoom, but usually it's just a bit easier for me to help you if you're in person. Okay. All right. So thank you guys for coming today. Hope you guys enjoy. If you're taking off right now, hope you guys enjoy the rest of your weekend. If you have questions on the project, please let me know. I'm always happy to help. And I will see you guys next week.
Good question.
Yeah.
For using finite difference or finite volume, is there a difference in complexity? I know, like what would you think would be easy?
I think in terms of just because the higher order scheme is a little bit easier to do in finite differences, I think that's probably gonna be the easier one. Because with finite volumes, with quick, you have to make the decision of which way the velocity is going, and so that just kind of adds another layer of complexity to it. And so I would say that, but then again, finite volumes is kind of fresh in everyone's mind just because we're covering it right now. And so in the past, what I've seen is it's about a 75-25 split. And so I'd say 75% of people usually does finite difference and 25% of people does finite volumes, unless you're a grad student. If you're a grad student, then you have to do both. But that's generally the split that I see. And when I ask students, that's kind of the rationale that they give me. They said higher order schemes, that's the one part we haven't gone over in class, how to do higher order with time marching. And so that's just a little bit easier to do in finite differences, just because there's only one scheme. And so there's no, but finite volumes is fresher in people's minds. So yeah. And so, that's all I'll say. And so I'll leave that choice up to you.
Thanks.
Yep. Mm-hmm. Since the time was based on t step, yeah, it's a good question. And so we have to maintain a separate variable for the time. And so that's what this t is right here. Yeah, so you make a good observation. And so the loop itself is on time, on t step, but this t step is just going to be integers, right? And so first it's going to be 1, then it's going to be 2, then it's going to be 3, and so on and so forth, right? But our time is not advancing on that same scale. And so our time is only advancing 0.1 seconds at a time, right? And so our time, we want our time to be 0, 0.1, 0.2, 0.3, and so on and so forth. Okay. One way that you can do it is you can change this loop right here. And so you can say that, this t step is going to start at 0. It's going to have a time step size of dt. And then we can have an end time of like 10 seconds or something like that, right? And so that way, your t step will represent time. But the way I've implemented here, it's a bit more traditional to how these codes are implemented in practice. And so you have a loop here. And so this loop here is all integers, right? So it's 1, 2, 3, 4. But then you keep a separate variable for the time. So that's what the t is. And so the t starts at 0. And then at the end of the loop, before you move on to the next iteration, you update it. And so you say t is equal to t plus dt. Yeah, so this way is a little bit more traditional to Matlab makes it a bit nicer because you can theoretically do it all just with the loop. But if you were implementing this in C++, even Python, I think, it'd be easier to do it like this too. C++, Python, I'll say Fortran. I know everyone laughs at me when I say Fortran, but it still exists. People still use it. This is kind of more traditionally how it's done. So we need if statements every time the t. No, the t is going to change automatically. And so the t is just part of the loop. And so by the time you reach the end of the loop, the t is automatically going to advance to the next one. Are you talking about the project? Yeah. So for the project, you're going to need an if statement because for the project, different events are going to occur at different times. Yeah. And so if you want to make an event, and so let's say that you want something to happen after t is equal to 1 second, and so you have if t is greater than 1, okay, then here you would have something change. And so I think one of the changes that occurs is like the velocity is going to change, right? And so if you have if t is greater than 1, you can have u is equal to -1 or something like that, right? And so with that, the default value of u would be this, okay? And so in the project, I think it's 0, right? So in the project, u and v start at 0, right? There's no velocity. But then once time gets past a certain threshold, then it's going to change the value. So it's u is going to be that, v is going to be equal to sine of 5 times t. And so this way, once t gets past 1 second, then your velocities will update. Yeah. So that's how you would do that. Yeah, it was either 1 second is it 1 second or 0.5 seconds? I think it's 0.5 seconds, right? Yeah, 0.5. Yeah. Yeah, so you would basically do it like that. Yeah. Oh yeah, Bob, I saw your email today. Yeah, I've just kind of had a busy afternoon, but I'll respond to you when I get back to my office this evening. Yeah. Yep. Mm-hmm.
For the project, we're starting with a uniform temperature of 50 degrees Celsius. How do we go about throwing that onto the governing equation? Is that the force, the source?
No, so that's going to be your initial temperature field, and so that's going to be different because normally we start with zeros, right?
So it'd be a matrix starting at 50.
Exactly right. And so what this is, this says that your phi, it doesn't really matter. Actually, you need to do it for Sol Kerr. And so in order to make it so that it starts at 50, right? Because right now what you're saying is that for this one, all the phis here are equal to 0, right? And so we want to change it to 50. And so there's a few ways you can do it. And so I think probably the simplest way is to do this. And so you can do 0 plus 50. This is technically like really bad syntax. And actually, let's see if it runs. Oops. Oh, it runs. Okay. Not one Excel. Go away. Or did it run? What is it saying? Oh, it's running. It's running, but I set the velocities to 0. Yeah. So this can work. It should work anyway. I think you do plus 50 here as well. And so that can work. If you show this to a programmer, he might throw up in his mouth a little bit because what you're doing here is that you have zeros. This is a vector, right? And so it's a vector, which is, n total number of rows. And then you're adding a 50 to that. So 50 is just a number. And so you're trying to add, a number to like a vector. MATLAB is smart enough to know that if you do something like this, you mean that let me add 50 to all the entries in the vector. And so MATLAB is smart enough to do that. But the more kosher way to do it, I guess, is to use a different function here. And so instead of zeros, there's another function called ones. Okay. So very similar to zeros, but ones here is gonna change all the entries to 1 instead. Exactly, and then you multiply it by 50. Yeah. So this is the slightly more kosher way to do it than just adding 50. But both should work. Yeah, but the way that you would implement that is through these initial conditions. Yeah, so I'll show you both. For the if statement time, do we need a new loop for it? No, and so it should all be handled just within one loop. So you should only have one loop to do time. Yeah, and then the if statement, think of the if statements as triggering certain events. And so once the time reaches past a certain point, then that event triggers, and then that's always going to happen for every time step after that.
Are we to add extra if statements, or is the starter code already covering
No.
all that?
You need to add extra if statements, and so especially for those time events, and so for those you need to add them, and for the Neumann boundary conditions too. I mean, I have the finite volume code here, but I think the first thing that happens is a window opens on the west, but it's not going to be for the entire wall, right? And so it's only going to be for a certain part, and so you need to change that with an if statement. So you would say if. I'm having you create like a variable for the y position, right? So if y position on the west wall is y position is greater than, I think it's 0.7, and y pos is less than 0.8, right? Then you can apply a different boundary condition just on that range right there.
Okay, I see.
Yeah, and so this is where you would apply like the open window boundary condition. Otherwise, you would do kind of the normal stuff, which is I think a zero flux, right? Zero flux boundary condition otherwise.
This is the same for finite difference.
Correct. Yes. Yeah. So finite difference, you have the boundary conditions in a separate loop, and so you would apply the if statements inside those separate loops. Yeah. Yep.
How is your final report version kind of affected by it if someone's doing both? Is it just like it's graded based on, let's say I do both, obviously, 'cause I'm
Yeah.
trying to give the best credit, but if I do finite differences and that's all correct and I write the report on that,
Yeah.
but then the finite volumes is incorrect, like how does that affect?
So the way I do graduate assignments, I don't factor graduate assignments into your grade. It's just kind of I saw that you completed it, it's mostly right, and then from there I sign the form afterwards.
I see.
So that's usually my policy with the graduate
You
assignments.
say that you could just write about one.
Yeah, but I was just asking like, because it's not, he wouldn't provide a second reference for like just a couple people. I was just trying to figure out like where the line is of.
Yeah. And so in the actual report, it only shows up in one section. And so you're going to write up the report for, even if you do both, you're going to write up most of the report with just one method anyway. There's just an extra figure where you compare both results.
Yeah, okay.
And you're going to submit both codes, of course, and I'm going to run both codes just to see. But yeah, so the way I do graduate assignment, it doesn't factor into the grade. It's just,
Cool. So just checking because I don't want to like find out that I totally screwed up one of them or something and then it all falls apart.
Oh, no.
I'm
Yeah.
like,
So
oh, no.
I that's the precise situation that I want to avoid.
Okay,
So
yeah.
and so yeah, that's the reason I do it the way I do.
Cool, thank you.
Okay, it's past 6:45, so I'm going to go ahead and start prepping for my next class. And so thank you, everybody. Thanks, Bob, for coming. So I'll see you guys next week. Have a good weekend.
Actually, when I'm the higher orders,